All right, welcome everybody. We're going to be talking about acceleration structures today again. And acceleration structures are used in 3D games for a variety of purposes. The main ones being collision, like finding out if two objects are touching each other, and for doing ray casts and other kinds of things where, like, you shoot a gun and you want to know what point your gun hits. Now, in our Raylib game right now, we just have, I believe, a vector of boxes. So if you shoot a gun, you in Raylib there's a function that tells you if a ray hits a box, but what you got to do right now, if you have no acceleration structure, is just check to see if that line hits every box. For every box in the world, run an intersection test between the ray and the box, and then it could hit multiple ones, so you have to find out which one's the nearest, and then return that as the point. And that is a stupidly slow algorithm, especially in a game of any reasonable size. So the good news is it's easy to tell if a ray hits a box, right? If you have a ray coming through like this, it's pretty easy to get that. There's a function for it in Raylib, but you could write it yourself. Like I have my CSI 40 students, first semester students, write this algorithm. It's not hard. Basically, you can either do parametric line form, but we'll just do mx plus b. Why not? And you've got a minimum x and a maximum x and a minimum y and a maximum y. And so what you can do is just, if this point here is 10, 20, and this point is 100 and 700, something like that. What you can do if you have a ray starting at, let's just say the origin to make life simple for us, starting at the origin with a slope of 1, what we can do is we can take, so this is 1x plus 0, so in other words, just x, right? So we can plug in 10 for the x, the minimum x, min x, is 10. And then we can see if 10 is in between 20 and 700. It's not, so we have missed the box. Okay. So the shot would have come like that underneath it. So you can just substitute in the minimum x into here and then see if the resulting is y is equal to mx plus b. You can see if the resulting y is between the minimum y and the maximum y. If it is, congratulations, you hit. If not, you missed. And then you can do the same for the minimum y, because it's possible for the ray to strike on the bottom as well. And so you could plug in minimum y, which is 20. And for that one, you have 20 is equal to mx plus b. So you solve 20 minus b divided by m equals x. B is 0, m is 1. So x would be 20. So where it hits the bottom row here, x would be 20. Is 20 between 10 and 100? It is. So in fact, the ray is striking the bottom edge of the rectangle. It's actually a very easy algorithm, and you can do this in parametric line form as well. It's a couple of statements. It's pretty cheap. It's not trivial, but it's pretty cheap. So even still, you don't want to do this on hundreds and hundreds of boxes. If your world has hundreds and hundreds of boxes in it, and your algorithm is see if the ray hits every single box, that's going to slow you down. Your frame rate's going to be absolutely garbage. Okay, so we need something called an acceleration structure to make that faster. And there's a variety of acceleration structures. We already talked about one earlier in the semester called BDH, where you have a person or something like that, and then you have a hierarchical system of boxes, kind of like surrounding the player. And these can be nested smaller and smaller to whatever detail of precision that you want. And if the ray misses the outside box, well, it missed everything inside of the box. But if it hits the box, then you have to check the next levels to see if those guys get hit. And it's like a hierarchical tree structure where you have boxes inside of boxes inside of boxes, like Matroska dolls, right? However that's pronounced. So what we're going to learn today, though, is a different kind of acceleration structure. We're going to learn briefly a grid, and then we're also going to go over the main topic, which is Quadtrees and Octrees. So a grid structure works well in certain circumstances. All of these acceleration structures have scenarios where they become degenerate, right? So for a grid structure, it works really well if your world's nice and spaced out. Like you got a house over here, you got a house over here, you got a tree over here, which looks like a lollipop. You've got a person over here, and you've got another house over here. I don't know. Okay. And you've got a person here, and they're shooting a gun in this direction, right? So what they can do is, first of all, check everybody within the local grid to see if they hit anything. Nope, we didn't. Great. Then you can find that point of intersection where the ray leaves the grid, and you can go into the next grid that it's connected to. And then you can check everything inside of that grid spot. The grid's empty. Miss. Okay. Move on. And so then you find its exit point, and then you check all the objects inside of this world, and it misses the house. So then it exits here, and then it goes through this one, and I'm going to curve it a little bit so it hits, but basically what you can do is you can walk through grid to grid to grid until it hits something. It's okay. Depending on, if we have 9 grid spots here, worst case scenarios, you're going to hit, like, what do we got here? 1, 2, 3, 4, 5 of them. This is probably the worst case for it. If it exits the world, then we missed, right? But there's a degenerate case where, like, all of your objects are in one grid, right? And now you're back to just checking everything, right? And so some people might fix that by just adding tons and tons of, like, just making the grid very fine-grained, right? And you just have tons and tons of grid points. Well, now, you're going to be entering and leaving, entering and leaving, entering and leaving, entering and leaving, entering and leaving over and over again, and that's going to tank your performance too. So when I actually made a game engine using a grid-based system like this, because everything was nice and spread out, it was a good match for the game that I was making. But I sat there and I played with it for a long time. Like, how big should a grid be? Should it be really big, really small? If objects are straddling multiple grid points like this, then it has to be within each of those, right? And so if you have a ray that goes through like this, then it's actually going to check to see if the ray hits that house 3 times, right? Because it's going to check in this grid, in this grid, in this grid. And so if you have things straddling the grid boundaries, then you're going to actually worsen your performance. And worse, I had the biggest problem that I had with it actually was when I had moving objects. And so the moving objects, I would basically figure out, okay, it was in these 4 grids before, if we have a house that's moving. And then if the grid moves to the right, I had to delete it from these 2 grids and put it into, like, the next, if it moved over to here, I would have to delete it out of some of the grids and put it into the new grids. But because I was using floating point numbers give you errors. And so every so often it would subtract in such a way that it would leave an entry for that house. Well, my houses didn't move, but it would leave an entry for the object in the old grid spot, because when you move things, errors accumulate and you don't exactly get the right number that you had before. So then I had to have every object track every grid that it was in, so I could be careful to delete it out of the old ones and then insert them into the new ones. Whereas what I had been doing was just, as the object moved, I would just subtract, like, the new versus the old and figure out the delta, and I was doing very clever optimizations and things like that. But when you do floating point math, it doesn't always add up the way you think it does. And so I would every so often just have zombie pointers essentially inside of my grid for objects that had already moved. And then when I was debugging it, I was just, like, very confused. Like, why am I checking to see if there's a robot in this grid when the robot's moved, like, over there? And there was no way of, like, deleting it out other than the robot kind of coming back through and then leaving again. So this approach works okay. And like I said, I tuned the grid sizes until I got the performance that I liked. I had plenty of objects in my world, and hit scans were plenty fast. Collision was pretty fast too, because again, you only have to check collision against things in your world. So if you have static objects, you don't have to check their collision. But if you have a dynamic object, like a person walking around, you have to check to see if it's hitting, every time you move, you don't want to just walk through a wall or a building or a tree or whatever. So every time an object moves, you have to see, am I colliding with something? And so the house and the popsicle tree, you don't need to run it every frame, but for every dynamic object that you have, did your grid spaces have to be perfect squares for that algorithm? I think they were. I don't think they had to be. It would just kind of be annoying, because the world itself was perfectly square. So it was a 4-player multiplayer VR game, and each player started in a different corner of the world, and there's terrain and stuff like that. And so it just, yeah, it was there were squares, but they don't have to be. It's just a little more coding. So every dynamic object, every time the object moved, every time physics ran on it, then you would have to see, is the new spot something you collided on? And if it is, then you have to handle collision. And the way that I did it was with a callback. And so I would actually have a function that was like a touch function, basically, called on the player, if it's the player here that's moving. And then the object, the static object, even though it doesn't move itself, it can still be touched. And so, like, if you want to have the ability to, like, break walls or something like that, or, grass that flattens when you touch it, or a tree that shakes, you bump into a tree with a giant robot, it should, like, react, to you. Then you can call, the dot touch function on the house or the tree or whatever, and maybe it'll react to you or something. And so what you do to do collision is for every, basically every time a dynamic object moves, every time physics runs, then you have to say for every grid point that I'm in, because remember, you can be straddling multiple grid points. The house here is straddling multiple grid points. The player could be across the boundaries, right? For every grid that I'm in, then check everybody else in that grid spot and see if I touch them. And if they are, call a callback on them, essentially. So the house's touch function gets called, the player's touch function gets called, and those handle collision. And you can either have it bounce or you can have it slide. There's like different ways you can handle collision, but basically that's the upshot. The physics engine would only look at the objects in the immediate neighborhood of the player, which is fast, right? If your world is all spread out like this and you've got maybe one or two objects, in each grid, you got a lollipop tree and a house, when the player is running around inside of here, he only has to check to see those two objects. Am I touching the tree? Am I touching the house? Am I touching the tree? Touching the house? Every frame. You could have like millions of objects out here in the world. Like there could be all sorts of trees and people and mechas and I don't know, bicycles and things like that. There could be millions of objects in the world, but when you do your physics, you only, you update your position based on your velocity based on your acceleration, which is a bad idea, but I did it anyway because I wanted the robots to kind of have mass and feel like they're slowing down and stuff like that. It was a bad idea. Acceleration's stupid in a video game. But you only, doesn't matter how many objects there are in the world. If you got two people nearby, it works great. Now, the problem is the grid structure doesn't work great if it's not sort of nicely, evenly distributed across the world. And that's where Quadtrees are going to come in, Octrees. Okay. So it's a similar concept. Except the grid sizes are not fixed. Okay. So you can have some grids that are bigger and some grids that are smaller. Octree is the 3D version of a quadtree. A quadtree is a 2D structure. For our ArrayLib assignment, we're going to make a quadtree. Why? Because unless you guys are going to change the design of the game, we are not going to be going vertical very much, right? Like Sean, I think, got jumping working, right? So you can go a little bit vertical. Maybe you can land on top of a platform or something. Megan did it. Okay. You can go a little bit vertical, but we're not going to have lots of things stacked on top of each other unless you guys are like changing the design, in which case we would need to use an octree. Quadtrees are easier to write because it's one less axis to worry about. You have X and Y instead of X, Y, and Z. It's just a little bit simpler. Okay, so let me show you how this works. So you start off and your world is just the world. This is the entire, this is the minimum of the world. This is the maximum of the world. Let's say it goes from 0, 0 to 100, 100. And there's nothing in it. There's no objects in the world. And then you start adding cylinders or whatever these cubic rectangular prisms we have. You start adding these to the world. And at a certain point, and the player's walking around, they need to know if they're touching something. You're checking, am I hitting 1? Am I hitting 2? Am I hitting 3? Am I hitting 4? And that's an order n algorithm, and you get really tired of it after a certain point. But there's only 4. Who cares? Just do an order n. Nobody cares, But if you've got 1,000 boxes, you got 2,000 boxes, you don't want to be checking if you're touching all 1,000 boxes every frame. That gets painful. Okay. So what we do is this is the root here. Root of a tree is always in the sky, you know, because computer science people have never seen trees before. That's why I took you guys to Yosemite a couple weeks ago, so you can actually see and like touch a tree, and like know what they feel like. You know, I have some great photographs of students touching grass and like they're like worried it's gonna hurt them. It's spiky. So, so what happens though when we start getting too many things? So what you can have is you can have something called a threshold, right? And you can have a threshold, and you can say that once you get, I don't know, once you get two objects into one of these grid points, or you can set the threshold at 10. This is again a tunable parameter. For this one, let's just set the threshold at 2. Just picking a number at random. Once you get two objects into the world, more than 2. So once we add the third object, let's say, once we add our third rectangular prism, then what happens is we subdivide, okay? And so with a quad tree, there's another kind of tree called a KD tree that does this a little bit smarter. You can do this in 2D or 3D also. The KD tree can like put the cuts horizontally or vertically at different spots. On a quad tree, you just cut the whole world into quarters, hence the name quad tree. Every quad tree contains a quad tree. So the root now has 4 children. One, let's call this one A, B, C, and D. So it's got A, B, C, and D. And then A is a leaf node, and so a leaf node means that it actually contains objects in it. So A is also going to contain, you know, box 1, B is also leaf node containing box 2, C is leaf node containing box 3, and D is currently empty. Okay. So now if we were to add a new box to the world, if we added it to D, that'd be fine. Like it's not over the threshold. So every quad tree contains 4 quad trees, or it's a leaf, one or the other. So if we add another box, let's say here to A, let's add box 4 here, that's fine. We're not over the threshold yet. Okay. Sometimes you set the threshold to 1. So once you go up to a second one, you subdivide. But that can create issues, like if you have 2 boxes that are like really next to each other, it'll like subdivide and subdivide and subdivide and subdivide, trying to find that spot where it can split the 2 into different quad trees. And so that's another place where KDtrees and so Quadtrees, the better version of a quad tree, is called a KD tree. It's more complicated, but it's better. It's called a KD tree, and the better version of a KD tree is called a binary space partition. And so BSP is better than a KD tree, more complicated to write though. So quad tree is kind of the simplest of these things. So if it's 2, do you loop over both? So at 2, we don't do anything. Our threshold is 2. So we're gonna be fine with it. Yeah. So do you loop over both? Sure. So the player is inside of A, right? And it's running around. And so in order to find out what quad tree we're in, the player is like, I'm currently at location, let's see, the split is at 50 here, and the split is at 50 here, right? Because it goes from 0 to 100, so the split's at x equals 50, y equals 50. And so the player is currently, let's say, here at 30, 10. And so 3010 is to the left of the vertical split, and it's below the horizontal split. So we are in quadrant, A, however you want to put it. And so it's just going to check. It's just going to check to see if it's hitting 1 or 4. Okay. And that's fine. Instead, you could have millions of objects in the world. At most, you're going to check to see if you're hitting whatever your threshold is, right? 2, whatever. Who cares? You guys understand? There's a problem if you're straddling if you're over a line, you got to check both sides, right? And if a box is over the middle point, like that, then it's going to be checked on all four of the things. So a lot of times you'll end up clipping, and so what you'll do is you'll actually cut your rectangular prism into 4 different pieces and put those individual pieces into the different quad trees. There's different ways of handling it. But yeah, if you have an issue, like you have a box with a box with a box, your quad tree is going to infinitely subdivide because there are, you know what I mean? Like there's more than two boxes at, these points here in the center. It's going to try infinitely subdividing down to whatever your smallest level of grid size is, like 1, and your performance is going to be terrible. So again, there's like, there's degenerate situations where these things don't work. Like you can't have nested things like that and expect it to handle it, right? Every object should be platonic, right? Do you guys know what a platonic solid is? Are you guys familiar with the term platonic solid? Right. So cubes, but really it just means they're just friends, right? So you don't have any boxes inside of the other ones. So yeah, you in other words, you don't have any complicated things like a box inside of another box, or things like that. Like they just are, like we're just sticking to cubes, but not cubes, rectangular prisms in this assignment. If you have anything like where they could be nested inside of each other, then yeah, you could group them or something like that if they're inside of each other. But basically, yeah, we're making certain assumptions or the code explodes. Okay, now let's add another box to A. So let's add box number 5 over here to A. So A is going to split. So all these leaves here are going to be pulled out. So and they're going to be reinserted. So A is no longer going to be a leaf node. A is now going to be split into quadrants like this. And we're going to have AA and AC and AB and AD. So the double A one has a little bit of 1 in it. AB is going to have 1 and 5 in it. AC is going to have a little bit of 1 in it and 4 in it. And AD is going to have a little bit of 1 in it. And the player, too, if that matters. You see how that works? So if you ever get too many objects in one of the quadrants, you split it. And you reinsert everything into the... You iterate over all the objects you had in the leaf, you reinsert them down. Whether or not you clip these objects and cut the 1 into fourths because it's across the boundary, you can do that. That helps stop that infinite subdivision problem by just cutting it, right? It's now 4 different boxes. It doesn't help if they're nested inside of each other, but if you have somebody straddling a quadrant, then clipping them is often a solution. And then that's it. And then if you add another person here, 6, then it's going to subdivide like that. 1's going to be in its own, 5's going to be its own, 6 is going to be in its own. If we add another person here, it subdivides. And so you can have some areas where there's nothing in it, right? Or there's one thing in it, right? So B, C, and D don't have a whole lot going on, right? But A, this whole area over here is super noisy, right? And so it subdivides down. And so what happens is that if you have a person over here and they just shoot a gun, I don't know, this way, you can find the edge of your grid pretty easily. You can check everybody inside of your grid. There's nobody there. Great, I missed. You find the exit node, you find the entry node, and then, okay, check to see if you hit 3. Nope. We exited the world. Miss. Okay. So this thing only had to check a couple, like it really only had to check 3. A little bit of math, figuring out where it leaves the node, where it's entering the next node. That's it. All these boxes over here, I could have a million boxes over here. Doesn't affect me at all. Now, could I set up a degenerate situation where all the boxes are stacked on top of each other? Yeah, I could. And so when I shoot at it, I'll end up having to check all million boxes, right? Like if I put all the boxes like that, like all on top of each other, not gonna help, right? It's not gonna help. You can always come up with degenerate, scenarios for each one of these things. So it really depends on what sort of game you're making. Are you making a big, expansive outside world? Are you making a quarter shooter? Quarter shooters like Quake, traditionally use BSPs to figure out, line traces and things like that. Quadtrees are very good if you have a lot of objects kind of moving around. You can rerun the quad tree algorithm pretty quickly. It's not too expensive to build a quad tree. And then, to do collision, you just check within your leaf, so let's say 2's moving around this way, it's just kind of like cruising around in a circle or something. Yeah, you just check all the other people within your leaf for the quad tree, and nobody else is here. All right, peace. I didn't hit anyone. There could be a million people down here, but it doesn't affect me. I don't have to check. I'm just within my node by myself, So an Octree is this with another dimension. Yeah, so in 3D. I'm not even going to try to draw that with my tablet skills here. But if you want to look at an Octree, doc-oc. Yeah, I guess. Yeah, so you can see the Octree is a cube, and then it cuts it into, it cuts X and Y and Z. And then you can see like this subtree down here, the sub-Octree down here doesn't have anything in it, so it's really big, but where you have a lot of objects, it subdivides. You have a lot of fine detail down there. But the areas where there's not a lot of stuff, it's sparse. Yeah, like that. All right. So you can have some areas that have a really fine grain, and that's where you want the fine grain stuff, right? You have a lot of objects moving around, so you have a lot of detail there. Parts of your world that are pretty empty, very low cost, right? So you can see here, anywhere you have a line, it'll subdivide down. And so the areas where there's no lines, it's just sparse. And then this area over here, see it subdivided into the quad tree here. So this one has nothing in it. So does that make sense? So these things are used extensively in video games. There's, the KD tree, like I told you, KD tree. Instead of dividing it into quadrants, they pick a splitting plane. And the first time they split, looks like here, they split vertically the first time. And then, let's see if I can zoom in on that. Proceed anyway. So like they're putting points in the world instead of rectangles, which is pretty common. So they'll split, the first splitting is line 1 here. And it looks like it's actually splitting on the point itself. So all future points are either going to be to the left or to the right of L1. And then they click here on P2 here. And so then the second split is going to be horizontal. And they're splitting it on the point itself, which is a decision, I guess, you make when you're working with points. I guess it makes sense. With cubes, you kind of want I don't like splitting cubes in half, because now you have it on both sides, and collision tests have to work on, which it defeats the point of it. But for a point, it's fine. And then for the next point over here, it split it. P3 over here, line 3. Okay, line 4, I guess. Okay, and then you can see P3 is to the left of line 4. P1 is to the right of it. P2 is on it. So I don't know. I guess they're saying if you're on it, you're to the right, maybe. P5 is to the, no, it's arbitrary, I guess. It's P5, okay, P1, P2. If P2 is to the left of L4, P5 should be to the left also, but okay, whatever. Maybe the line's going up. I don't know, whatever. It's on the line, it doesn't make any difference, I guess. So you see how that works? Like they pick a splitting plane vertical first, then a splitting plane horizontal, and then the other side horizontal doesn't have to be at the same point. It could be at a different altitude. And then after that, you split it vertical, and then you split it horizontal, you split it vertical, you split it horizontal. And you can figure out where the splitting plane should be based on the geometry. The bridges people did a pretty cool KDtree. thing here. Yeah, so you see they split, and they split, and they split, and they split. And the visualization. Oh, whatever. That's the idea. All right, it's basically a quad tree, but instead of you dividing it by exactly in the middle every time, you pick the splitting plane. Okay, and then a BSP is the same as a KD tree, except the lines don't have to be horizontal or vertical. So if you have a KD tree, that's a KD tree there. A BSP tree, you can pick any angle you want. And so that's obviously much more computationally expensive to try and figure out where the splitting plane should be, but you can make it much more optimally because you can divide, you can shoot a line this way and put these bunnies on one side and these bunnies on the other side. You shoot a line that way. Whereas if you had to do vertical and horizontal, you're going to be clipping those bunnies in half over and over again. So it looks a lot like a BVH, but a BVH is a series of bounding boxes nested inside of themselves. Which an Octree, it looks like it, right? Because you have, it kind of looks like, yeah, it kind of looks like voxels or something. But it's splitting, like the Octree splits the space into cubes. And the BVH wraps the geometry in nested cubes instead. Okay, so that's kind of the conceptual overview of grid-based acceleration structures, Octree, Quadtree based acceleration structures, and then just a little brief bit on KDtrees and BSPs without really going into how they decide to split, because that's it's actually kind of an open question, right? Like there's a lot of heuristics that people use, like if you've got a bunch of cubes in the world, and some of these could be at weird angles and stuff like that. Like how do you split it on a BSP so that you get half the people on one side, half the people on the other side? Because there's an infinite number of splitting planes you can use, right? And so you can feasibly run your BSP program forever, right, to find the most optimal, way of cutting the world up. A common heuristic a lot of people use is they'll just pick like the longest edge in the world, and then they use that as a splitting plane. And then on this side, we're done because there's one object left. On this side, probably this one, and then we split it there. This guy gets clipped into two different boxes. On this side, we've got two boxes left, so we'll split, understand? So maybe this will split here, and then on this one, split. Maybe here, something like that. And we end up with one rectangle in each one of the different regions. But yeah, your BSP computate, like generating it can take infinitely long, right? It's there's a lot of heuristics to cut the world up, but there's not the optimal solution, I think, is NP complete. It takes effectively infinite time. For Quadtree, it's very simple. When you exceed the threshold, cut it up. So for the KD tree, you have to come up with some sort of cost heuristic to figure out which column or which row you want to cut on. And so it could be quite computationally expensive to figure out exactly where the splitting plane should go. But if you have a well-defined cost function, then you can run it just on every row, every column, and then you're done. Okay, so I will write the Quadtree code for you guys. I plan on having that done by Tuesday for you guys. So right now you've got a vector of all of your boxes in the world. I will write the acceleration structure for you. And then when you want to do collision, you're only going to have to check collision against people in your leaf or leaves if you're straddling, if you're on an edge or something like that. And then you can then that'll allow you guys to put as many boxes as you want in the world, assuming, and this is again why I wanted to give the lecture today, you don't do something degenerate like having 5 boxes, 5,000 boxes all encapsulating each other on the same spot, because then the Quadtree is going to broken die. So, you're expecting another Raymond Cry? No, I'm doing it. Oh, did you want to do it? I mean, I feel like I should do this one. So, uh, you'll try this class. How about you let me do this, and then you guys work on the actual game dev part of the game class. This is I mean, this 50B is more of a game engine class, but Quadtrees can be tricky. So maybe on Tuesday we'll go over the code for it and stuff like that. Yeah. The amount of effort you're putting into this just to be mod credit. Yeah, I don't know. I'm thinking about giving you guys both like depending on how much time you guys spend on this, I might just make this like your whole grade, something like that. I don't know. So we can talk more about that, but yeah, like basically it'll be both your Unreal project and your mod project, just given how much time you've spent on it. So it'd be kind of mean to make you guys do a project. I mean, I know. Well, let me ask, Megan. You've put a lot of time into your Unreal project. Do you want to not have to finish that, or is Megan still here? So I know you were kind of looking forward to finishing the Unreal project, but I kind of like the way that you guys are working right now, where you're all checking things in and out on GitHub, resolving the merge conflicts, things like that. Like, I feel like this is actually a really good experience for you. But doing something on Unreal Engine, is also valuable. Probably running the project for us. Okay. Okay. Let me think about that some more. I'll come back to you guys on that. But yeah. I think just if we push on this Raylib project more, then that could just be your grade for everything. We'll see. Let me think about it some more. Okay, so that's it for 50B today, and I'll come back in a second for 50A. Peace.